Hi, this is Thomas. Welcome to math class. We're looking at the calculus topic of integration. Integration is closely related to differentiation. It's actually differentiation in reverse. So we're going to begin with the concept of an antiderivative. And we're going to calculate an antiderivative by using the process of differentiation in reverse to get from a differentiated function back to the original function. Before we look at examples, let's look at notation. We use notation for a function f of x. If our function is f of x, then f prime x is the derivative. And capital letter F of x is the antiderivative. Let's start by considering the power rule for differentiation as our example. If I know that the function of x is x to the power of n, then the derivative function is n times x to the power of n minus 1. So the process is I take the value of the exponent, I place that in front of the x as a coefficient, and then I reduce the value of the exponent by 1. And my two-step process was 1, exponent to coefficient, and 2, reduce exponent. So for my antiderivative, I'm going to use a reverse rule, the reverse power rule. So if I'm starting with the function x to the power of n, I want to go in the opposite order. So my first step will be the second step in reverse of the power rule. I will increase the exponent. And the second step is the first step of the power rule in reverse. I move the exponent to denominator. Instead of multiplying with a coefficient, I'm dividing. So in looking at that process, the antiderivative, first I increase the exponent. So I have x to the power of n plus 1. And then I move the exponent to the denominator. Now notice that the exponent is now n plus 1. So I'm going to divide by n plus 1, which is the new exponent value. That's antidifferentiation. I'm using the reverse process of the power rule, which gets me from a function to differentiation. The reverse power rule in reverse gets me from a function to the antiderivative. Now let's work through an actual example. In the example, I'm going to start with a function. I'll differentiate, and then I'll antidifferentiate. The idea of antidifferentiation, differentiation in reverse, should get us back to where we started. So let's look at the function 2x to the power of 3 plus 5x squared minus x. And I'm going to start with my derivative. F prime of x equals 6x squared plus 10x minus 1. Now what I want to do is change my terminology. Let's consider f prime x to be f of x as the now base function. And we're going to take the antiderivative. For my first term is 6x, increasing the exponent by 1 to 3, and putting that value of 3 as the denominator of the term. Next term, plus 10x. 10x has an exponent of 1. I increase that exponent to 2 and divide the term by 2, minus 1. 1, it has an exponent for the x variable of 0. So I will increase that exponent. X to the power of 0 becomes x to the power of 1. And I will divide that term by the exponent value of 1. Now I'll simplify to 2x cubed plus 5x squared minus x. And if you look at the top of the screen, we now have arrived back at the original function. So it worked. From function to derivative, then considering the derivative, the base function, taking the antiderivative, gets us back to the original function. Now let's consider a similar function in a second example. F of x equals 2x to the power of 3 plus 5x to the power of 2 minus x plus 4. So I'm adding the constant plus 4. I'll go through the same process. I'll take the derivative to get to 6x squared plus 10x minus 1. Notice that while the original functions aren't the same, the derivatives are the same. So now, when I consider my derivative to be my main function, and I take the antiderivative of that function, I'm going to end up with going through the exact same process. In the end, 2x to the power of 3 plus 5x to the power of 2 minus x. And now when I compare to the original function, I don't have the same function. I'm missing the constant positive 4. Now for what we're calculating in both of these examples, we're calculating the antiderivative. Both answers are correct. In a more precise expression of this relationship between the function and its antiderivative, we want to show that there is an additional value in both of these functions. In fact, we didn't see it in the first function, but we will in just a moment. There's an additional value that we want to take into consideration. And so now we're going to go from antiderivative to the concept of the indefinite integral. And I'm going to put indefinite in brackets because we will often refer to the indefinite integral as simply the integral. The integral of the original function is 2x cubed plus 5x squared minus x plus c. And the plus c is the recognition that there could be a constant that is present in the original function that we need to take into consideration in the integral. So we see that directly in the second example, plus 4. I can add plus 0 to the first function, and there's a constant as well. It simply has a value of 0. So by adding plus c to the end of the integral, I take into consideration any constant in the original function that would have dropped off in differentiation. My representation of the integral is an elongated s then the function, which for our example is 6x squared plus 10x minus 1 dx, meaning with respect to x, equals our result. And so the full read of this expression is the integral of 6x squared plus 10x minus 1 with respect to x equals 2x cubed plus 5x squared minus x plus c. This ends our first lesson on integration. We've learned how to calculate the integral of a function using the reverse power rule. And in our next lesson, we're going to learn how to integrate exponential, logarithmic, and trigonometric functions. I'll see you then.